Hello and welcome back everybody to my video series on implementing the Ray Tracer challenge by James Buck in Rust while learning the language, which I've never used before. And
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
until now it was quite an adventure, it was fun. We did even have some visual progress in the last session, which I will quickly recapitulate here. So what we did in the last session was we put together all the different parts we implemented before in order to use our vector and point implementation as well as our canvas implementation to calculate and store image data to actually create the trajectory of a projectile which we calculate, which is influenced by gravity and wind from this side here, which is then pushing it down to the ground. And we are actually generating this as a ppm image file and writing it to the disk. And as you can see, it is actually working out quite nicely. So the next chapter we are now going to tackle is the chapter containing matrices. It's a whole chapter about implementing the basics and basic transformations we later on need regarding matrices. So what are matrices actually? Matrices are essentially, let me create a file here for this where I can then put all this stuff in. Matrix rs. Matrices are essentially kind of a grid of information. So what we would have is like something like 1, 2, 3, 4, and maybe, don't know, 4, 5, 6, 7, 8, and 9, 0, 1, 2. And here maybe 3, 4, 5, 6 again. So this would actually be a matrix, a 4x4 matrix. A matrix of floating point values. In this case, they are only integers, but we are going to store them as floating points, which actually represent some form of structural data. A 4x4 matrix therefore has 4 rows and 4 columns. Matrices are quite heavily used in rendering systems, and not only in ray tracers, but everything which does render something, which does perspective transformations, which does transformations at all, I guess. You would use matrices a lot. I've used them in 2D space as well as 3D space before. And they are actually quite useful because you can easily apply certain mathematical operations with them to a vector space. So what we can do is we can essentially use take a point and, for example, move it by a certain distance in 3-dimensional space by multiplying it with a matrix, and we will get a new point, and this point will be moved. Or we could, for example, rotate a point in 3-dimensional space easily by applying another sort of matrix and multiplying it with it. And this is actually quite useful for all our different computations, because there is some stuff regarding matrices which is really useful for us in this this sense, as it makes life a lot easier for us. We can, for example, have something like the inverse of a matrix. We will implement all this now in this chapter, which will essentially take back a certain operation we've done before. Like if we have the inverse of a rotation, it will rotate the whole thing into the other direction, and we can actually calculate stuff like that. Furthermore, we can, and that is something mostly every 3D rendering system uses, is we can multiply different matrices together to create one final matrix, which when applied to, for example, a vector or a point, will result in all of those operations before combined, but would only take us one matrix multiplication operation per vector then, and not like 20 if we would have 20 different operations before. So it's actually quite efficient as well. That to be said before we really start regarding matrices and why they are useful and we want to use them. So let's get started with matrices. We need, as always, to register. No, that was the wrong file. Where is it? librs. We need to register our new file here, mod matrix. No, matrix. There we are. And do we actually need to import something here? Yeah, maybe we will need to import this later on, but okay, let's take a look at this. The book actually tells us that we should implement a matrix with, as it is foreshadowing that we need it for a lot of different operations, mostly with base types of the language. Furthermore, we need matrices, mainly the 4x4 matrix, but we need 3x3 and 2x2 matrices as well. So now I'm not 100% sure how to do this. I would like to implement it in a way which simply uses native arrays in Rust, because I would guess they are most efficient in memory layout. However, I'm not 100% sure on how to implement this in a way which would easily work for different dimensions or different sizes of matrices. So we would need to implement a 4x4 matrix, a 3x3 and a 2x2 separately. Or we would need to implement one data structure which for example, has an array 4x4 in size and then only uses a portion of it for the others. Yeah, I'm not 100% sure on how to work with that. What actually happens, let me test this first. No, if I do something like type matrix, let's call it matrix 4, is an array of floating point 64 values, and it is actually 16 of those. So I can define that. Can I now define some implementation on matrix 4? Can I do something like, for example, fn new? It should be new should return a new matrix 4, and let's just do something like, let's return an array of zeros here for now, something like that. Only a single inherent implementation marked with lang array is allowed for tn primitive help. Consider using a trait to implement this method. So I guess now in this case matrix 4 is equivalent to this type, and the system doesn't like me implementing a method for it. That's kind of bad. I hoped that it would work like that. Furthermore, I would really much like to later on access this like something like, if we have a matrix, I would like to access it like this, I guess. Something like give me row 0 and column 1 or stuff like that. So I'm not sure how to do this. We could of course do something like, I guess this would work. If we are using an array for that, we could do f64 by 4 and 4 of that. I guess that would work. Yeah. So the question I'm thinking about here now is, how do we implement all those operations? So we have this type alias here. I like that. So we have better readability. And now we have a trait which would be matrix 4 as well. No. Let's call this matrix 4f, and this should be matrix 4f as well. So I'm not sure if there is a clash, if it's allowed to be named as well multiple times. Yeah. So matrix 4f. Let's call this matrix 4f type actually, or let's call this matrix 4f array. So now we have this one, and we want this trait, and this trait actually, let's check what the first thing is. Maybe we can even implement, I would love to implement do I want to implement a new for it? I guess we have done it for everything else, so we should most likely have it here as well. So let's define that there should be a function called new, which takes the rows, I guess. Row, which is an array of, or better said rows, which is a matrix 4f array. And it returns a matrix 4f array, I guess. And we could even implement it directly here and say, okay, it simply returns rows. It's kind of weird to do that actually, but this way we could actually instantiate it in a feasible way. Maybe we want to have maybe we want to have this differently, like just all the values in one go. Yeah, let's think about this. So of course what we need first are tests. So let's do this. Let's copy this actually from this one, because I always forget how to specifically define this. There it is, CFG test. And then we have our first test. Let's close this one, let's open this one, let's close this one. Just a little bit cleanup. So, okay. Now this needs to be closed here. We are importing this stuff, and now we're doing test. And what actually would be our first test? The first test is actually ensuring that we can create a matrix, and that's exactly what we want to implement first. So let's do this. Fn constructing and inspecting. Constructing and inspecting a 4x4 matrix. This is our test function, and this function actually creates a matrix. So let's matrix equals matrix 4f new. Is this actually, can we actually call it like that on a trait? Let's see. Maybe we can. So now we are doing it like, what are the values here? 1.0, 2.0, 3.0, 4.0, followed by 5.5, 6.5, 7.5, and 8.5, followed by 9, 10, 11, and 12, and the last row would be 13.5, 14.5, 15.5, and 16.5. So can we format this? There's a mismatch there. Yes, I've Type annotations needed. Cannot infer type. Node. Cannot satisfy. Matrix 4F. Yes. I guess so, because this is a trait. And so we need to do it like matrix 4F type. Oh no, I called it array, not type. Type annotations needed. Cannot infer type node. Cannot satisfy matrix 4F. So maybe I should do it. I should do it like this and call this one matrix 4F new. And this one is a matrix 4F then, and this is a matrix 4F then, and now we should be. Wait a second. If I do this away and I simply do now impl matrix 4F new for matrix 4F. Now it should actually be able to call this. It is. Okay. Okay, let's but we really do not need this, and I think we should not do it this way. I don't like this new. I would very much prefer it to be simply like we say it is a matrix 4F and this works. Yes. Yeah, we should do it like this. And I'm now starting to wonder if we should have implemented vectors and points like this. Maybe we will go back and refactor it at some point, or we will change this up quite a lot if we are running into problems there in the future. So let's see. We don't need this matrix 4F new anymore. We can remove that, but no. But oh yeah, we can remove that. So we have only defined the type yet. So let's do our testing here, and the test says that we should now assert that we can easily access all of our data as expected. So I guess let's call this M, makes things a little bit shorter here. So if I access 0, 0, 0, this one should actually equal 1.0. So let's copy this quite a lot. So let's check, is it checking a certain, yeah, it's checking row by row. So that makes sense. 2, undo, 3, and then we have, let's actually copy this, and now we can replace this with a, come on, we can replace this with a 1. What is happening? Replace this with a 1, yes, and then we copy it again. And we are replacing this with a 2, and we copy it again, and then we are replacing it with a 3. So now we can actually check all those values. It should be here 2, 3, 4. Then it should be 5.5, 6.5, 7.5, and 8.5. And then we are with a 9, 10, 11, and 12. And then we are again there with a 13.5, a 14, come on, 14.5.5, it's a 15.5, and a 16.5. So actually, let's check if this works as we expect it to. Test matrix. Let's run those, and they fail. Why the hell do they fail? We have a .4 somewhere in here. There. So what we actually have now is we have written a test which tests the array syntax and access of Rust itself, because we haven't really implemented anything. On the other hand, we are ensuring that our type is working as we expected. So I guess that's quite okay here. Now the next tests we need are that we can represent a matrix which is actually a 2x2 matrix and a 3x3 matrix. So I guess we just need to define those as well. I've just decided for now to represent them as the same array structures, and we will see how many of the operations we actually need to implement for them are overlapping. So maybe we can share some code there later on, or find a different way to do that. We will see. I don't yet know, and I don't want to take it to care about that yet. So let's write another test here, which is fn 2 by 2 matrix ought. There's a G missing, ought to be representable. So we can just say let M matrix we can actually say it's a matrix 2f, and the matrix 2f should essentially be it should be -3.0, should be an array of arrays. There we go, and it's -3.0, 5, and 1.0 minus 2.0, and I've missed the .0 there again. So now this should actually be our matrix. Can we actually split this up into multiple lines, or is the auto formatter just putting it back for us again then? Yes, it is. So yes, it is unused for now, no problem. Now we are asserting equality. Let's do it. Let's copy those. And those should be -3 and 5. And then we need the same thing for the second row, which is then 1 and -2. Let's format this. No, I don't want to open stuff. I want just to run the tests now. And they are passing. The next test would be that a 3 by 3 matrix is actually representable. Let's do this quickly here. We have a 3 by 3, and this is then it's a 3F matrix here, and it now has the values -3, 5, and it has 0 here, and in the next row it has a 1, -2, and a -7. And then it has then it actually has a 0 in this third row, and a 1.0 there, and another 1.0 there. So yeah, double split up to the next line as well. So what we now need is we need another value here, which is actually now a 0, and we need to check for another value here. Come on, which is a -7, and then we need a whole other row, which will be 0, 1, and 1. So let's compile this and test this, and it seems to run. Yeah, so the next thing is that is implementing equality of the matrices. And that is something I'm not 100% sure about, because the book is telling us that we should make sure that equality works out for floating point matrices, which might be different with reasoning to floating point deltas. So floating points have a limited precision, and we might end up with two, in our sense, identical matrices which nevertheless have a little bit different values. So we kind of need to use our fuzzy comparison for this as well. But how do we implement this on array now? Okay, can I override the partial equality on this specific kind of type here then? But then I would override it essentially for all these array types. Can I do this for a trait? Can I? No, that doesn't make sense. I would be implementing one trait on another trait. That wouldn't make any sense. Yeah, that's kind of, I don't know, a little bit. Maybe we need to implement our own equality function then there, and use that. Maybe we should do that. Maybe I'm overthinking this, and I should just implement it on this because we will only use it in this way in this application. But it could actually have. Okay, let's check if I can even do this. So can I implement partial equality for matrix 2f. Is this actually an allowed operation? Okay, there is a conflicting implementation. So there is already an implementation for that. And that's essentially what I feared would happen. So maybe now is the time to think about implementing this fuzzy equality trait. Maybe I will just start here with it and say, okay, there is this trait called fuzzy equality, or FuzzyEq to stay within the thing. I've thought about this before for the other types. Instead of implementing partial equality, just implementing fuzzy equality, and maybe we should do this now. So I guess we should implement this fuzzy equality trait here and say fuzzy equals, I guess. And wait a second, the partial equality trait, what does it actually return? So let's check that. So maybe we should implement it exactly like this then, and say simply FuzzyEq. So this is a function which needs to be implemented. It's FuzzyEq, and it is self with a reference to other, which should actually then be a template, a reference to some other thing, and we can implement this. And what we give there is we want fuzzy not equal to, which will get self as well and other as well, and we can this one we can, oh, it should give you a bool back. And now this one should simply be self dot not self dot fuzzy eq with other, I guess. And this should of course give you bool as well. So this should allow us to implement fuzzy equality, and let's move this to the util, and maybe we will rename util now to fuzzy. Okay, so we have this here. It's essentially a public trait because it can be implemented by others. There we are. So now we have this, and now we want, what we want is essentially we want let's now implement this here. So we are use how did we use something like create? We can, yeah, I remember. You can use so oops. So we are using create util, and we want for now we want everything from this, and now we are going to impl fuzzy eq for matrix 2f, and this would actually be there would be a function called FuzzyEq self. Oh, no, we need to implement FuzzyEq for another matrix 2f for matrix 2f. So yeah, and now we have self, which would be a matrix 2f and we would want to implement it for other no, we don't need the type here, it's clear. We need it here, matrix to f, and we are returning a boolean. So, and now we are simply returning here, let me see, we are returning here f64 FuzzyEq, and we put in there self 0 1, I guess, yeah, and other 0 1. Yeah, come on. And I guess we are ending this with let's actually do this like this and there, and now we should be able to copy it at least. We need it 4 times, yes, exactly. So now we need it with 4. No, this actually should have been 0 0. This is 0 1. This is 1 0 1 0, and this should be 1 1, and this is actually what we should be returning there. So now let's create a test here, as we are expected to do. It's test fn. Actually, matrix equality here is only implemented for 4x4 matrices in this test, but I like to have it for everything. Matrix equality with identical to 2x2 matrices. So let's implement this, and let's just assume that this check works. So let's just have a let m1, which would be our not really sure about these values. Let's just put 1 2 3 4 5 6 7 8 9 in here, followed by for example 1, and in the next row we have 2 and 3, and this should work out. And now we have the same again, but as a different structure in memory, but with a change here to 0. Actually, those are different, but should actually matrix equality. Let's call it matrix. Let's actually do 2 tests of this. This will later on be matrix fuzzy equality with identical matrices, and yeah, I guess this should work. And now we are doing assert. Yeah, we actually cannot use assert equals then now. We would need something like assert fuzzy equals. We would need our own macro, but for now let's just do something like assert m1 FuzzyEq m2. And this should be a mismatched types found. So we do need to put a reference in there. Okay, we need to put a reference in there. So let's just check if this actually runs. Yeah, it runs. That's nice. So now let's really do this. It runs as well. And now we should be able to first of all, I need to fix this with identical. No. With identical. There is this D does not belong there, and we want equality with almost identical 2x2 matrices. And here we really have 2 identical, and here we have mostly identical. So that would be a great thing. Now I really much would like to create a macro ourselves, like assert fuzzy equality. And I think I will take a look at how this equality macro is working. Assert equality Rust macro. I want the not metro. I want assert. There it is. I want to know how this one actually is written. Give me the source code of that. Maybe we can simply copy this out here and simply adapt it to our needs, because I'm not sure about all this can we just put it there, and now everything's broken. Well, unused macro definition. Okay, can I do a do I need to mark this as public as well? Okay. Okay, I need to export it then. So this kind of makes sense, I guess. Macro, what was it? Export. Okay, what it did tell me. Macro export. Okay. So let's try this. Macro export. Okay, so now I want fuzzy equality. Let's make a macro mostly copied from assert EQ without, come on, understanding all of it. Maybe needs to be revisited in the future. So okay, it seems to me that we have this left expression and this right expression, and I have no idea what this means actually. I guess that there might be another comma after that. And then we are creating a match. So we have a left val and a right val, and so I guess this is actually the comparison part. So I guess we could do if left val dot fuzzy EQ no, fuzzy not equal right val, then do all this panicking, and this should maybe work already, and we can replace this here as well, and I guess so. Maybe let's check this. So it should be possible for me now to do assert fuzzy EQ M1 M2. Cannot find macro assert fuzzy EQ in the scope. Importing this macro. Create assert fuzzy EQ. Have you added the macro use on module import? No, I did not. So I need obviously to now have something like macro use here. No. So do I need something like assert fuzzy EQ here to specify? No. Okay, I think I need to read up on how to import macro Rust. Let's take a look of that. How to import macros in Rust. Is there, okay. So I guess it is okay, macro use. So I see. Now can I use it now? Cannot find macro assert fuzzy EQ in the scope. Still not working, I guess. What I need to do here is use create assert fuzzy EQ, something like that. And then this doesn't throw anything at me anymore, but it doesn't work anyway. So no, this error originates in a macro. Unresolved import. Oh, the similar path exists. Core option. Yeah, maybe because I've now copied it from, I guess this is not wrong, as I copied it from this core thingy here. I most likely need to do this, and then I most likely need to have this annotation above it there, which was above the original one as well. So yeah, just a little bit of trial and error programming here, and what was it? It was, let me check. No, yeah, we left those there. So I guess we need to do this as well. So let's put this there. Feature gating and stability checks. Allow internal unstable side steps, feature gating and stability checks. Yes. But I do it because I want to do it. So does this work now? No. Side steps, feature gating and stability checks. Yeah, but I want to do this. I guess I'm already getting the idea behind that, and it would make things a lot better. So a lot more readable, especially. So let's remove this, and maybe let's yeah, let's just, oh no, let's just put it there. We have now this here, and it's essentially the same as yeah, we could do it like left expression, which we had already there, and we wanted a right expression, so it's right as an expression. So I guess I get that. So what we are actually going to do is, oh, we can, that's nice, we can actually put macros and macros, yeah. So we have those hygienic macros. I like that. So I don't 100% understand why this is there. It's most likely just because just there to make sure that we have two references actually. I would love to somehow check if we have this fuzzy equality thing on them, but maybe that is even possible. I don't know. But as far as I can see this one, it's just we can remove this and then simply do a panic there with can we actually put formatting there? Yes, we can. Asserting that two values, asserting fuzzy equality is not fuzzy equal to, and let's just do it this way, and now we should be able to just put left val and right val in there, shouldn't be. So, and now we should be able to do this here as well. Maybe we simply don't allow this. I'm not using it anyways, so who cares? So let me mark this as not really sure what I am doing here, as I don't have a great understanding of macros yet. Feel free to fix or enhance in the future. So now let's check if this is now working as it should. No, it, oh, something did something there. Okay, so there is a warning, unused imports, because Yeah, do I need to import this now or not? I cannot find macro. So maybe what I need to do is something like as it was there, that I need to do a mod use macros. Was it macro or macros? Macro use. Yeah, macro use here. And maybe now this still not working, so and that's I don't like that. Can I export and import macros Rust? Let's check. So okay, after they have been declared. So do I actually need to do the following thing here? Do I need to do this? And this is why it's not working. Okay, now it can't find it, I see. And what is if I do now macro use here? Is it no? Oh, now it works. Okay. That is what we did wrong there. So that is something. Let's check. Okay, that's actually really nice. So now we can do assert FuzzyEq M1, M2, and this will work here as well. And will it actually fail if it is different? Let's change this one to a 4, and let's now. Okay, so now we should see that panic deck asserting fuzzy equality is not fuzzy equal to. I like that. That's nice. So it's working. So let's do something like, let's add source util, and let's created fuzzy EQ trait with corresponding assert macro. So, but actually we need to source, no, not matrix lib. There is something as well what we need. It's yeah, we need to kind of split this one up. Yes, we want this, and want to split this. Let's do it this way then. So yes, we want this one. So git ci minus amend. Is it amend? Yeah, it is amend. So because we now need to change the import order, and now we can put this one back there. And now we could go on here, like I guess I want to try something else. I want to implement. Could I implement? Let's check this. Impl fuzzy equality on type F64 for F64. Can I do that? It seems to me I can. So fn fuzzy equality self. Now most is it. Will we get a reference there? I think we will get a reference there because we specified it as reference. Other reference to F64, I guess, then. So bool, and what happens if we now put this there? And then we say self which is a dereferenced self and a dereferenced other, and do it like this. So if this is actually working, I then should be able to change this here to something like FuzzyEq, doing it this way. In order to use this, I would essentially need to do something like this. Mismatch type, expected bool, found. What? Okay, so this is referenced automatically then, and this is, okay. Yeah, okay. Let's actually do this. So let's do this and then do that there. FuzzyEq like, oops, all referenced other 0, 1. And let's copy this 2 times and then have this one as here with 1, 0, 1, 0, and 1, 1, because now we are recursively using this trait. I like that. And it should actually compile and work out as well. Yeah, it works. So I like that as well. So let's maybe let's put this epsilon there then somewhere else. Maybe in this, I want a const epsilon here, then epsilon here, which is actually this epsilon value. Missing type. Okay, so I need this F64 type here. Yeah, constant is never used. So we are now doing epsilon here. So yeah, this actually works. And we are doing epsilon here as well. So it is now inside this util thing. So let me get this one, add source util git ci implemented FuzzyEq for F64 and extracted epsilon. So right now I would like to rename this util thing. Yes, I would very much like to rename it. Rename. Still no idea why this damn renaming operation does not work. And I would like to call it FuzzyEq, not fuzzy double, FuzzyEq. But this causes certain things to be different now, because now, as I see it, I have to do something like now I need to import mod FuzzyEq, and I'm not sure should modules module naming best practices Rust is they are naming conventions. Modules snake case. Okay, so let's name them snake case. It's okay for me, you know, don't have a problem with that. But now I need to, of course, FuzzyEq import this. Do I even use this here? Fuzzy, yeah, I am using this. Okay, so first let's have everything compile again. So FuzzyEq, and the tuple should FuzzyEq as well. So then this should actually cargo test. This should actually still compile and all our tests are running. So let's take a look at this. Let's add source FuzzyEq. Let's add yeah, let's all add, we need to add canvas, lib and tuple, add source canvas, rs, source lib, rs and source tuple rs, and remove source util.rs, and there we go. Move FuzzyEq trait to module FuzzyEq instead of util. So we've done this. Now I guess we can start refactoring this by implementing not partial equality, but yeah, by implementing fuzzy equality. So yeah, let's actually refactor this. Should be quite easily doable by simply using the FuzzyEq treat here and calling this fuzzy, and then we should already be going, but essentially we should change this to FuzzyEq and do it like this, and let's do the same thing here. Self y FuzzyEq reference other, and let's copy this 2 times because it's faster to rename that than to do this again. ZW. So now we've implemented this, and we can remove that, and then we have all these assert equality thingies, and essentially we should use this fuzzy comparison for all of them. So let me just quickly replace all of the assert equal calls with assert fuzzy equal calls. There we go. And I would hope this does still compile and run. Let's check. It compiles, it runs, all the tests are fine. Nice. So git add source tuple, git ci migrated tuple to use new FuzzyEq trait. Come on, there we go. So the next thing we need to move over is canvas. Shouldn't be that hard as well, because I guess we have the same kind of partial EQ implementation. Yeah, for color we have it. And we want a fuzzy equality there. So now this method is called FuzzyEq. And we are doing what we are always doing here. We are now comparing this using the fuzzy equality trait. So this is, come on, fuzzy EQ. Give me a reference to that, and then we have blue here and blue here, and we can remove that. Yeah, we definitely need to specify color here. So we want one color with another color compare, and now let's assert equal. Let's see all those things, because I guess essentially we want this, we would replace those, we would want to replace those, we want to replace all of them, I guess. No, those we do not want to replace, I guess. So yeah, we need to, but at least we want to replace all of them for colors. So let's replace them in this area until we are going to creating a canvas, and there let's replace those, and there we do not want to replace those. Actually, here we want to replace it. I actually like that we now need to specifically test for those fuzzy equalities in our tests, so we are sure where we want fuzzy equality and where we won't want, where we don't want it. It makes things a lot more explicit, and I like that. So this is a fuzzy equality test as well. Expected result, those are not fuzzy equality tests, not fuzzy equality tests, not fuzzy equality tests. So no, let's run the tests. Oh, there were some warnings there. Yes, still importing partial equality. Yes, and now I guess we don't need the... yeah, I think it's right. We don't need this implementation anymore. So we have removed all of its... nice, dead code detection. I like that. So let's commit that. First of all, source fuzzy equality and add source canvas. Refactored canvas to use new fuzzy equality trait. There we go. So now I guess, oh, let's just ensure we are not using something within our, no, we are not using something like the fuzzy or util imports in our executables. But then I guess the compiler would have already complained about this. So yeah, so that's nice. Let's clean up our things here a little and then get back to what we actually were going to do. We were about to ensure that those matrices can be compared, and for a 2x2 matrix we already implemented it, so we need to do the same thing, I guess, for 3x3s. Fuzzy equality with identical 3x3, or a matrix equality. I guess now we can, now that we have it explicitly, we can drop this from the naming. So there we go, 3x3. I want it there as well, and I want exactly. So now we need to specify something like this and something like this, and yeah, we need another row, of course. So let's just have 5, 6, and maybe 7 dot, something like this. Let's copy this over here, and let's is this the with almost identical ones? So can I find M2 in this scope? Yeah, of course you can, because I've just copied over this one, and there we go. And in this case it should be identical, and in this case maybe, oh no, maybe do this, maybe do. What I wanted to do was just remove some precision here, and yeah. So now this should not work. Let's compile it. Actually, it should utterly fail because, yeah, defines an item, fuzzy NE. Perhaps you need to implement it. So what I now need to do is actually implement the trait, the fuzzy equality trait for our 3F matrix. And actually this one should then be a 3F, and it should be almost the same, but we need a column and a row there in addition. So now we have added this column there, and we should, oh no, and we should be quite working on this one, and now we need it for the next row as well. So let's just replace those with a 2 and those with a 2 as well. So actually, I guess there are a lot better ways to do this, like iteration and stuff like this, but why should we iterate over something when we can do this? It should even be faster. So okay, what's now? It's complaining about something here. Function is never used. Function is never used. Did I? Oh yeah, I actually missed the test annotation there. Yeah, so sounds good. So let's ensure the same thing is valid for 4x4 matrices as well. So 4x4. Okay, it does not work out because, yeah, because we did not implement it yet. I see. Let's take this one and let's implement it for a 4F matrix. There we go. We need another column there for each of the rows. So we now have a third column, a fourth column with the index 3 as we are 0 indexed. So let's do it this because we have another row as well. There we go. And there we go. Let's format this. Let's run this. Yeah, so that's quite nice. Okay, so we now have the possibility to define matrices and to compare them with their equality. And essentially, there is another test here which should ensure that we can determine non-equality, but I don't know if we really want to implement this test, as we are quite sure we can, due to the fact that we implemented this fuzzy equality, which comes with a non-equality as well. But okay, let's create such a test. Why not? Why not? But only for the 4x4, I guess. Matrix inequality with identical 4x4 matrices. So inequality with non-identical 4x4 matrices, and yeah, why not reuse them and make them different by putting this one there. So assert fuzzy EQ, so that would imply that we need a not equal. Is there actually an assert? Oh, there is an assert not equal, so I guess we should have this as well. Why not? Should be easy enough to implement now, as we have this as a basis. We can simply say if left val equals right well, and we call it not equal, asserting fuzzy inequality is not fuzzy is fuzzy equal to. Yeah, so it's like this then, and this should then actually be able to do this here. And if I'm compiling this now, it should work. Yeah, it runs. Nice. So let's add this one. Source fuzzy equals, git ci, implement assert fuzzy ne macro for inequality assertion. Okay, so another thing we have now done is we have a really basic matrix data storage implementation, I guess. Oh, I should add a command there. Git add source matrix, git ci, implemented basic matrix 2f, 3f, and 4f data types, just like this. So let's push this. And maybe we should add the output thingy to, you see, output ppm. No, not output ppm. I wanted to add it to the git ignore. So let's just add output.ppm here to the git ignore. New line. There we go. Git sc. Git add git ignore. Git ignore, git ci minus m, ignore generated output.ppm file. And let's push this so that it does not always linger around there in our diffs. So yeah, there we go. So now we have a very basic matrix implementation based on on arrays in Rust, and I really much like that. And we even implemented now our fuzzy equality, which I was thinking about like I did it the first time. So I could now remove the to-do here in our tuple implementation, and I like that very much. I like to remove to-dos. Okay, now we have a, a new to-do, but we will get there, I guess. So I like this a lot better than it was before. Maybe it was a very horrible idea and we should have stayed with partial equality, but we will see in the future. At this point in time, I like it a lot better. So, and maybe it's even a horrible idea to do all this stuff with matrices that we are currently doing here, as just using them as this data type, this simple array data type with hard sizing. Yeah, we will see. I'm not 100% sure, but I just guess from my experience with 3D rendering that we will be mostly using 4F, so 4x4 matrices within the code that is to come there. So I think we are quite safe by maybe not implementing every operation for every of those matrices. The book even states in this chapter that we only need to implement the next operations for a 4x4 matrix, which is actually then like we will be implement multiplying matrices next, and then essentially building the inverse of a matrix, which needs a lot of work to be done before, some mathematical operations on matrices that we need to calculate and that we need to implement there before we then can create the inverse of a matrix, but it will be very useful later on. Yeah, so as it is getting late here and we are already at nearly 2 hours for this chapter, I will now take a break here and maybe grab a bite to eat. And yeah, maybe if I'm in the mood for it, I will come back later on and do the next one, the next session here on implementing all this mathematical stuff I just talked about. And of course, I will do it together with you, and you will be able to follow me. So maybe I will just be back and do the next session later on this day even, or yeah, maybe one of the next days, we will see. But I will be glad I would be glad if you would join me then there again. And yeah, don't forget to subscribe and like this video if you didn't already. So the subscription is kind of useful so that you get notified if I'm posting a new video, and the like is more a thing that is useful for me to see that you like those videos, and for the YouTube algorithm to better place this in searches and stuff. So yeah, thanks for now, and see you the next time. Bye.